This session is covering three sorts: bubble sort, insertion sort, and selection sort. First up is bubble sort. Bubble sort is a very naive algorithm. It's not very efficient, but it's very simple to implement. A very good introduction to the world of sorting algorithms. We'll be covering it for all three: arrays and with linked lists. So the idea behind bubble sort is if you have some collection of numbers in a sequence, you want to be switching them together. So you want to be, I'm not on a pen. You want to be switching pairs with the idea that you switch the larger forward. So larger values, and you want to make them propagate to the end. To the end. So the idea is you will go through each pair, compare them, and if the left one is bigger than the right one, you'll swap their positions. And you'll keep doing that. You then look at the next pair, do that, swap their positions, next pair, do that, swap their positions. Again, each time, only if the left is bigger than the right. When each pass of that then, so going from one time from left to the right, we'll put the largest element in the sequence to the end of the array, or end of the data structure. So that'll cause... so this causes the largest to bubble, hence bubble sort. And that's for every iteration. Okay. So example with an array. For this one, if we want the pseudocode for how to do this, we want to first off look at these two pairs. So we want this pair and this pair. Then we want this pair and this pair, this pair and this pair, this pair and this pair. And we're looking positional here, not value, because at some point, for example, 4 and 2 are going to have to switch. So even though this shows 4 and 2, it'll actually be even though this shows 2 and 6, that'll be 4 and 6, because 4 is going to end up in this position, and 2 will end up in this position. So we want to do this, and then we want to do it again, because we're going to have multiple things. After each pass, we're only going to be moving one of the things to the end. We're not going to know the position of everything else. It could be we're done. Could be that we're not. It depends on which case we're using. Okay, so where's my algorithm? There it is. So we're going to want some data structure array. We're going to call it R. So this array is that. And we're going to want to set up a while loop. We could formulate this as a for loop, but for simplistic pseudocodes purpose, I'm going to have it as a while loop. So we're also going to want a counter variable, so I equals 0. And we're going to want a Boolean flag called swapped. And this will help with efficiency. There's no reason redoing the whole iteration if you've gone through the entire thing and didn't make any swaps. So while swapped is true, we're going to keep going. So while swapped. And then the idea is we're going to have to set swapped immediately to false. Because we only want that to be true if we have made a swap. So the default case is no swaps are made, it sets to false, and then later we'll set it back. So we're going through this, and then we want to be looking through the entirety of the array currently. So we're going to say a for loop. So for, we're going to call this counter j. So for j, this is going through the range of 0 up to I. Because if you think that if you go every iteration you go through this, you're going to be putting the biggest value to the end, then there's no point to go to the end again. If after the first iteration you know that the last one is already sorted, the next time you only want to go to the one before that, the next iteration, the one before that. So for I equals 0 through... j equals 0 through I. We're going to go through this. And I'm definitely going to need more space. For everything we're going to have to do, we're going to have to look for this pair, and this pair. So if we're looking at J, this is our position through the list. We want to look at J and J plus 1. And we want to swap their positions only if our J is bigger than the array of J plus 1. So if J is bigger than R of J plus 1. So we look in the next position. Yeah, I'm totally going to need more space. I'm going to move these first, so we don't have to do it in a second. Drop my pen. You go down there. Okay. So if this case is true, so we have a swap needs doing, we're going to have to take the elements in this position and put it here, and this position goes to here. Depending on language, and how you could, depending on language you're writing in, depends on what you're going to do. For simplicity's sake, I'm just going to say that, oops, we're going to use a temporary variable. Right, temp equals R_I, then J, my bad, J, and then RJ equals RJ plus 1, and then we're going to do RJ plus 1 equals temp. So you just swap these positions around. If you're using Python, for example, you could do a simpler thing, which is just this. Same thing. And then, because we have done a swap, we also want to set swapped equals true. True. Can't spell. And then last thing to do is do I++. At the end of every inner loop, we want to increment I a bit. So what this will do is you'll go through, if we do an example, where I equals 0, swapped as true, entering, swapped as false. Now for 0 through I, so, oh, no, not I. I made a mistake. Not 0 to I, because I set to 0 initially. For 0 through the length of R, minus I. My bad. So the length of this is 1, 2, 3, 6. Minus I is 6 as well, because it's 0. And we're going to presume exclusivity, so we're not actually going to reach 6, so we're going to go 0, 1, 2, 3, 4, 5. For this array, we'll go through each, we'll check. So we're going to look at this one. They are not equal, so we don't enter the thing. This one again, they are, not equal. This one is less than. Now this one is greater than. We're going to enter the swap. We have now swapped, so we know what we're doing in extra iteration. Looking at these two, we have now 4 here rather than 2. 4 is not less than 6. It's not more than 6, so this stays the same. 6 is more than 5, so now we have 6 here, 5 here. So there's 2 here. And then 6 is more than 3, so we'll have 3 here and 6 here. That's after the first iteration. We have 1, 2, 4, 5, 3, 6. So 6 has bubbled to the end. Next iteration, we will increment I by 1, and then do 6 minus 1. So we won't even be looking at this bit anymore. This is locked in. So we'd only be going through this position to this position. Oops. And that'll go all the way through until eventually we'll make a pass where no swaps are made, and we'll know for certain that there are that this list is full. Sorry, not a list. Array is fully sorted. If we were using a linked list, then it is pretty much the same structure. It's gone. Pretty much the same structure, but the manipulation of the array has to be swapped out as well as the access. So we're using the same things we did last session, where we have array is each element in the element. Try that again, shall I? For each element in the linked list, we have next, previous, and data. Using that syntax. So again, we're going to say that list equals this. We're pointing at this one, so we're going to say list ahead. So we're looking at a cur of a cur of list dot head we want to go through this. We want to be looking at this one. We want to then be going through every single thing starting off. So we're going to want another swapped equals true. Don't know why I made that capital. And then and also I equals. Oh no need for I. Never mind. So while swapped, we want to do the same thing as before. I've accidentally closed my notes. Let me give me a sec. There we are. Okay. So while swapped, we want to be setting swap to false again. And then we want to be going another loop. Before we had a for loop because we were accessing indexes. Here we're accessing dot next. So we want to be going until whatever our current is set to null. So while we want while current does not equal null, we want the same thing. We want to be doing the same test again. We want to be going through checking if if cur.data is more than current.next.data. If it is, we want to be swapping them. So in that case, we would want another temp variable. We would want to set. See, this one is cur. Then we want to be doing. So what you get for not writing out the notes for the linked list part. Whoopsie. Yeah, so we want to be swapping these around. So, if for example, this position, we want this one to be pointing now to this one. So this has to go all the way over here. And this one has to go all the way over here. And then these two arrows have to be swapped around. Nice and simple. Okay, so that means that cur dot, not private, there. Cur dot next equals cur dot, I can't write, next dot next. So that's that's overshooting on next one. We're going to want to set that one's previous to that, so that means that cur dot next dot prev equals cur. So that's set this one to there and this one to there. We now also need to set this one, which we have lost access to. I should have done this to be temp equals cur dot next. There we go. Now we need to set this one to its right position. So 1 needs to be pointing to 5 as next and previous to null. We ignore the null? I think we can ignore that null. So then temp dot next equals cur, and then I'm running out of space, and then cur dot prev equals temp. So now we have this in position where those two have swapped places. Similarly as before, there's nothing we need to do if there's not similar. We just leave it be, continue on. However, because of a linked list, we do have to be incrementing cur. So we need cur equals cur dot next. We're going to the next one, and then also, well, before we had to be incrementing the I, we don't need to do that now. There was a point with a linked list, without knowing what we've already sorted, this is slightly less efficient. Because we have no counter how deep we can go. What you could do here then is add in an I of how deep you've been to do. You've sorted the last one, so you then count in this, and how deep you are does not equal how far you should have been. However, that overcomplicates it quite a fair bit for only a slight increase in efficiency. So for simplicity's sake, we're going to leave it as this. And then, oh, important step. I'll type swapped equals true. Because now we want to be doing another iteration. And then that'll go through all the way. And then again, we'd have the swapping of all the pointers in the correct position. And our output at the end would be a fully sorted linked list in ascending order. Specifically, both of these are for ascending. If you want to descending, you swap this around. Are you back up here?
Yeah, I'm all here.
Okay. Oh, yes, you are. Okay. Do you want to take on?
Yeah, sure. So next one is selection sort. This one's pretty easy to grasp. It's not too hard of a thing. So what we're going to do is in a list or an array. So we got an array below, just to use an example. We're going to find the minimum value. Then we're going to essentially, so what Prudence said the thing was remove from inputs. So let's say remove from array, and then append it into a resulting array. So we'll say append in result. So essentially what we're going to do is find the minimum and append it to a new array in a theoretical sense. And then you repeat that until, you keep on repeating that until you're done. So if we look at it from an array standpoint, it's not too difficult. You'll kind of see what's going on. So we can do this with for loops. So we're going to have a nested for loop because we're going to need to be going through essentially two sets on the same array. So we'll see now. So we've got, just to start off, we can say n is size of array. To stick with that, we'll just say r is the array as well. And we're going to use lock, which is just location, which is the one that we're just looking at currently. So let's just say in a for loop, we got for I. So we're going to start at index 1, as Prudence did in the lectures, and we're going to go to n minus 1. And you'll see why in a second. So we begin, and we're just going to set the location that we're looking at to be whatever I is, as that's where we're at currently sorted in the array. So the array essentially becomes two halves, one that's unsorted and one that is sorted. And we're going to use the left side as sorted and right side as unsorted, because we're going to make it going in ascending order. So we got lock equals I. And then we can start the next for loop. So we can say we're going to define another variable j. So we got for j, and that looks at the next variable over from lock. So we can say I plus 1 to n. So this is going to go from location to the end of the array. And we're going to do. And we're going to say if the array of j, so index j, is less than array index of the current location that we're looking at, then we're going to make lock j, because lock just needs to be the minimum value. So we start off where I is, and then we essentially go through the whole array to check which is the minimum, find the minimum, and put it in lock. And then it's, at the end of that, once we've gotten to the end of the array, we can essentially just swap lock with I. So let me just create some more room. So we can do that in the same way that we did it in the bubble sort. So I believe we used the temp variable, so we can say temp equals I equals r lock, and then r lock equals temp. That swaps it around, and then that's the end. So going back to the top loop just quickly, we can see we've gone from for I1 to n-1. Well, if we know that the everything before the last item in the array is sorted, then we know that the last item is going to be sorted, because like it's gonna essentially push the biggest item all the way to the top, as well as pushing the smaller things to the bottom, if that makes sense. So your last item's also going to be sorted, which essentially saves you an iteration in the long run, which will really help you on really big arrays. But in the really small arrays, you'll hardly notice a difference. As we can see, the time complexity is n squared because we've got the two for loops. We got a for loop over here, and we got a for loop here. Both of those pretty much iterate from using n-1. Not much difference between n-1 and n, so we can just say the time complexity here is just O of n squared. Okay, hope that makes sense. Now we're going to go to linked lists, which is a little bit more involved, but hopefully should still be pretty similar to the array. So let's have a look what we're going to do here. So we can look at saying we need to know, we basically need to start from the left-hand side because we're going ascending again. We need to know first if the linked list is empty. So what we could do is if, and we know we have the head pointer, so we can say if head double equals nil, then we could just say empty list. We could just stop. We could actually break out of the loop. Well, we could break out of this method, and we can stop the computation. If it's not, then what we can say is, well, if not, actually, I'm going to quickly just move this over slightly so it's indented. If it's not empty, then we can say, well, the current node is head, as we're looking at the first value. And then we can do a while loop for this one, because while loops tend to go nicely with linked lists. So we got the next value, so current.next does not equal null. Now let's have a look. So begin. So we can basically just say that for now, like we did before, our min value is just going to be our current node, and the node that we're looking at next, we're just going to call node for now, as that'll just be quite trivial down the line. And then we're going to start our next loop. So now we can say, while, because node is going to be the one that's moving up and down the list now, we can say, well, node is also not equal to null. Now we can sort of start looking for our minimum here. So we can say if node.data less than min.data, then we can say min is node. Min is node. And then what we can do then is, after every time we've gone through this, we can just do node is node.next. And we can end this portion of the loop. And so now, essentially, that is our finding the minimum. Pretty easy, just as like we did the array. Then what we can do is swap the nodes. So in the lectures, Prudence said you can either swap the pointers or you can swap the data. I find just swapping the data easy, just like an array. So we can create a temp variable. So we can just say temp equals node, I think is how it needs to go. Oh no, it's, sorry. Temp equals current, current equals min, then min equals temp. I think is that how it goes? I'm pretty sure. What do we do? But what would we do above? Oh, sorry. No. We'd say node equals temp. So that swaps the data.
You'd have data, wouldn't it?
Dot data? What do you mean?
Well, if we're trying to swap data, we'd be referencing their data. So.
Oh yeah, sorry. Yeah. Well, we can say just temp is just a temporal variable for the data type. So then we could just go.
Null data and curl data.
Yeah, we'll do that now.
Also, I massively overcomplicated this, didn't I? Sorry, everyone. This is much simpler. Same process applies to bubble sort.
Oh, I messed up there. And then we need to do. Okay, so then we can do dot data, dot data, dot data, dot data. Then we just essentially just swapped all the data. And say if you had something like frequencies or something like anything about a node that isn't pointers needs to be swapped here. So like we've had in the past assignments where it could have been like a frequency of something being used, that would also need to be swapped. Otherwise you're going to have a really malformed list and it's not going to make sense and you're going to get incorrect outputs. And once you've done that, you just do, you just increment current. And that's it. So just to go quickly back over it, we've got checking if the list is empty and stopping if so. If not, setting the first value to what the head would be, just because you're starting at the left side of the list and making it ascending order going from left to right. And then you're going to look through those nodes, begin, set the current node that we're looking at to minimum, and then make the next item in the list equal to node. And then you're basically going to iterate with node right the way through the list and just check which is the minimum by checking the datas. And then you update the minimum with the node if it ends up being less than what the current minimum that we have is. And that'll move, and then essentially we just swap the data then. When we swap the data, so we swap minimum into where the node would be, and where the node was, you put the data that we've just taken from current, and then you do current.next. So pretty easy. A little bit more harder with linked lists, but I don't think it's too difficult. You can look over the stuff afterwards if you didn't quite get it. But yeah, and it's also the same time complexity because it's the same sort. But yeah, I think that's it. I think we can go on to insertion.
Yeah, I think so. Okay. This time I'm preemptively going to move linked list. Pardon me. Okay. So we'll call this purple. Actually, I have purple out. Yeah. Okay. Insertion sort. I quite like insertion sort. It's a cool sort. Whole idea behind insertion sort is looking backwards. So if you have, let me copy this and I'll use it as an example. If you have a sequence of numbers, and you're looking to sort them, the whole point is that you start rather than the beginning, but one in. I'm not on a pen. On one in. And you'll look backwards. And the idea is that if you look backwards and see that the element you're looking at is less than what you have, then you'll look even further backwards, and you'll keep looking backwards until you either hit the start of the sequence or you hit something which is smaller than what you're looking at. So you'll get this chain of sorted things that you'll build up from the left to the right. So the idea behind... Sorry, let me have a drink. My throat's a bit sore. Okay, so you'll have a chain of sorted numbers building up from the left, and over time you'll increase that as you go on. So here, this would stay as it is because 4 is greater than 1. Here, though, 2 is less than 4, so 2 would be going to the left. And then it would look again, and it would say, oh, well, 1's greater than 2, so it's not going to go any further, and it's going to put 2 here rather than here. It will remove it from where it is and insert it to where it should be. Then it will continue on. It will look at 6. And 6 now looks at 4, which is the next position in the list. 6 is greater than 4, so it stays as it is. It will look at 5. 5 is less than 6, so it will go over. 5 is greater than 4, so 5 will get put here. Then look at 3. We have 3. 3 will look at 6. It's less than 6. 3 is less than 5. It will continue on. 3 is less than 4. It continues on. 3 is more than 2, so it will go between 3 and 2 and 3. 2 and 4. Pardon me. So the idea thing is pulling up incrementing the more sorted list as you go on. And even better in a hopefully single pass, going from left to right, rather than having to repeatedly go over the same path like bubble sort does, where it goes over the list again and again and again, each time sorting it by one. Insertion sort does it all in one path left to right, but in several then nested iterations backwards to the start. So if we look up on the array pseudocode, you want to be starting past the first. So rather than normal this being 0, you're starting at 0. You're going to be starting at 1 for clarity index. So we have an array equals this. We want to start I equals 1. And then there is just a for loop. So for actually, rather than say I here, I'll define I in the loop. So I equals 1 through then length of array. So r dot length. How's this purple readable? Can people read this? Making it impossible to read.
It's a little hard to read, but
I will switch to another color. What's this?
Yeah, that looks a bit better.
There we go. So what was it? Yeah, 4. And then we want to do I equals 1 through, and then the length of the array. And similar to selection sort, we're going to have a location of where we're looking at. So we're looking at so we have a location. Actually, I'll stick with Elliot's thing. Go look. So we have a location that's set to be where we're looking at first. We're going to say I minus 1 because we start off looking at the previous index, and then what we want to do is repeatedly, iteratively, continue decrementing I all the way down to 0, or until we find something which is greater than what our currently thing is, which is Ri. So 4, and we're going to want another increment. Actually, not 4. Pardon me. While, because we're doing conditional, because we have two conditions here. Either our increment is we find something bigger than what we're looking at, Ri. So what's the nice way of doing this? So array lock is smaller than array I, and the other condition would be if we hit 0. So while lock is greater than 0. Is that the right way around? Elliot? Normally I just run the code and see if it worked, but it's a pseudocode.
Let me check what I sent you.
Right, while he's doing that, I shall move on.
I've got while lock is greater than equal to 0 and array lock is greater than key.
And key is just this. So yeah, oops, wrong way around. Okay, so while this condition is true, which is while we haven't found something that to signify that we should stop, and while we haven't hit the start of the list, we're going to keep going backwards to the start and finding where we should move the thing we found. And while we've done that, we just want to be decrementing lock. Yes. So lock minus minus want to be. That's not clear because you minus equal 1 because minus minus doesn't look right. And then what we also want to do is pardon me. What the hell is that? Can you take over for a second? Something's going on.
1 second. Okay, so far we've got a loop that goes from 1 to the array length, and so what we've got to do is, at the moment, we haven't really assigned what the key is, or we've got lock, just not the key for now. So quickly just going to say that that key symbol that he's used is just what we were looking at the start. So it was I, just to avoid confusion. So we're looking at it, and we want to see where location is greater than equal to 0, and where the location, the data in that location, is greater than the key. So when that is true, we're essentially going to want to shuffle the array down. So we got array lock plus 1 is now going to be what where the location was. So we're basically just like moving everything to the right temporarily, and then we're going to decrement lock as we go, because if we're moving it to the right, we're essentially moving the value that we want down to the left. And then once we've moved location all the way to 0, then we've looked through the entire thing. So then what we're going to do is look at array lock plus 1, and we're going to make that equal to key. And let me see if I can visually show that to you, rather than, because that's quite a confusing explanation.
I'm back. Sorry about that. There's a terrific noise in the background. Don't know where
So
it is.
essentially what we've done is, so we're looking at, let's get some data up. So we've got 34, 10, 64, 51. That'll do now just to prove a point. So we start off looking at this number. Well, yeah. So this is the number we're considering here at the moment. In the algorithm, we're gonna first have this number as our as what we're looking at, and we set our location to 34. So we're looking at 10, location to 34. So we always have our location set to the first one first. So then what we're going to do is we're going to look at to see if the data in that location, so here, is greater than or equal to here. Now what we can see is, yes, that's true. And what we're going to do then is swap them. So that means that this array lock plus 1, which is 10, now becomes 34. So this essentially just goes like that. And so what we've done then is we're essentially moving it all the way up. So we've now got array lock plus 1, so that's the data is equal to array lock. So that means that if we're looking at this, array lock plus 1 is 10 is equal to 34. So we've got 10, 10, 64, 51. That's what we got for now. And then we decrement lock. So lock was already at 0. Now lock is at -1. So what we're going to say is array lock plus 1 is now equal to the key. Well, -1 plus 1 is 0. So that means that we're going to put 34 index 0. No, 10. 34 index 1, because we started off with lock as I minus 1, which is 0. So essentially what we do is we go, well, this is already here, so then it goes here. So then this becomes 10, 34, 64, 51. Kind of confusing to look at, but it works, I guess. I don't know. This one's a little bit of more of a confusing algorithm, but I think Cami will do a better explanation at doing it with linked lists. So if you want to move on to that.
Yeah. So about my disappearance.
We can go back over at the end if there's any questions, if it's quite confusing.
Yeah, so for linked lists, this algorithm actually gets a bit simpler, though you still have to be messing around with pointers and stuff, or data. Simply because linked lists are good at insertion, and with an array, you have to be messing around and shifting over every element. So you have to swap and then swap and then swap. Whereas for a linked list, it's just delete the element and then reinsert it wherever it needs to go. So for example, where's a good instance where that would happen? Yeah, let's do 1 and 4. Well, I want something in the middle, so let's do 3 and 6. So we've gotten to 3 and 6, and we're seeing that this, okay, 3 is less than 6. So by that point, we had the situation as 1 and 5 would have been swapped. Then 1 and 2 and 5 would have been swapped. And then 1, 2, 5, 6, 3 is the situation we have. And what we want is 1, 2, 3, 5, 6. So the point is of this, essentially we have to delete 3 from this position. So 6 has to then be moved to point to 4. And 4 has to be moved to point to 6. And then 3's pointers have to be set so that 2 points to 3 and 5 points to back to 3. Pardon me. Which is a simple insertion and deletion, which we covered in the last session. So I'll just be using them as if they were a method. The algorithms are up on YouTube as well as the whiteboards in the 108 chat. So this algorithm, I'll be referencing those. Have I switched back to the same color we were using before? No. Okay, so looking at this, we're going to have to first figure out if the linked list is structurally sound. If we have a null linked list, then we don't want to be doing anything. If head does not equal null. Because if it is null, then we have no linked list. We can just ignore it all. There's nothing to sort. If it isn't null, then we have something to sort, at least one element of. So we want to start working. So as you can see here, if we're looking at this, we want to be looking at this as our current. We're starting here. Sorry, not here. Here, because we want to be looking back. And to get here, we want head.next. So we're going to call this node equals head.next. So now we're looking at this. We're going to check. And this is where the outer loop comes in. We set up, this is where we start. And then, essentially, since the end condition for this loop is us reaching the end of the linked list, we want while node.next, or node itself. Node does not equal null. So we'll loop until we've hit the end of the linked list. Now we want figure out what we want to do. Well, we want to be looking backwards and checking if this is less than this. So if node.data is less than node.previous.data, well, in that situation, we want to enter the inner loop, where we start iterating backwards to the start. And there's two stop conditions for this. Either we have this situation where we hit something that we're greater than. So while I need to go into the second variable, because we're going to have one to search through. Let's call this current. So while current equals node. Okay, so while the current.data should be pref, shouldn't it? Yes. So we're looking here, we're looking at this, we want the previous, we're saying is this less than. We're going through all the way and saying is the previous one still less than what we're looking at. So less than node.data. We'll keep going along. If it is less than, more than, our stop condition is less than. This is our while condition, which means it has to be true when we still want to continue going. So while code.data is more than node.data, we want to keep going backwards. However, there's also a situation where we get to null, so you need this similar condition here. So and then cur does not equal null. So keep iteration. Keep iterating backwards through the linked list until one of those fails. And in that situation, when they do finally fail, we'll have a current that is where we should stop. And between that, we need to be doing current equals current.pref. So this is just a traversal up until we get to this point. When we're out of this, then we say, okay, we're at the position we want. The 3's gone all the way over here. Now we need to insert it and delete it from where we came from. So we want to be inserting to current. So imagine this as things. So the first one is we want to insert 2, so that it will be after this, and then the second argument is what we want to be inserting. So you want to insert node after current. And now just do all the stuff that we explained last session for us there to make this algorithm a bit simpler, because otherwise we'll be combining 2 in 1. And then we also need to delete node from the linked list. There we go. And that, if I've not missed a step, which I don't think I have, will allow us to go through and move each thing to where they need to go, and then continue on. Oh, I should do complexities. I've been forgetting to do this, haven't I? Yes. Okay. So if you're looking at this algorithm, we have 2 loops. The first loop is going through from up to n. Second loop is going through up to n as well. These are all n squared, aren't they, Elliot? I forgot to write them down. I forgot this is the thing we should do.
Yeah.
So it is n squared. Thought so. For some reason, I got in my head that one of them was n log n, but no, that's a different sort. Is it merge?
Merge, yeah.
This one is also O of n squared. Same algorithm. We're still doing 2 loops, which have to go through, in the worst case, the entire thing. In reality, probably wouldn't be quite that bad, but isn't good enough to be in a different category. So are there any questions?
All good, yeah?
All good. Easy,
Cool.
mate.
I don't know why my stream goes blurry sometimes. It's weird.
It seems to be when you move the entire like canvas,
Yeah.
everything just bitrate like hits the deck immediately.
It's just Discord, like every stream on Discord.
It's like Discord just heavily compresses stuff, so like when there's movement, it shits itself.
Oh, okay, the squares still show up. I was thinking maybe that was the squares moving, but I can't get rid of them.
No, insertion sort's a funny one. That one's very. It's overcomplicated.
Yeah, it gets overcomplicated for arrays, especially. I think for linked lists, it's not so bad
No,
because
it's
they're
not.
made for it.
Yeah.
Arrays
But
seem to kind
arrays-
of go against their purpose.
The shuffling of the arrays is quite hard to understand in terms of like a code way.
In fact, for is it
you're like
n squared for a linked list?
Um,
Because it's constant time to insert, so only if you have to go all the way back to the start, and you don't do that for every single
actually,
one.
hang on. Let me.
Is it n log n?
Yeah. Because you're still nesting a loop with at most n iterations.
True, but is that for you can't go back all the way to the start every single time.
Yeah, but you've still got that in like that big loop at the start that goes through the whole thing.
Yes, that's n, but then what's the complexity of the inner loop?
Well, it's gonna increment from n to 1, so it's gonna be n squared at one given time, because you're gonna go through the entire thing. So it's technically still n squared.
Okay, so it's the same case where it's nowhere near n squared in reality, but in the same classification because worst case.
Yep.
Okay. And I don't think I mentioned it as well. Oopsie, what I just moved. Bubble sort again is n squared. Which is odd. You'd think, okay, bubble sort knife approach, very simple to code. Probably not as bad as the other. It's probably worse than the others. No, they're all n squared.
Yeah, they're all n squared for this one. I like selection sort the most out of all of those. Selection sort's the nicest.
Yeah, I like the way insertion sort looks. Like there's a. I forgot to get a picture of it, but let me quickly have a look.
Oh, it looks cool where it inserts at the right place given the context of the like linked list, but you know, when you're doing it with arrays, it's a bit rough.
Sorry, guys.
I liked it visually. I just thought it was quite nice visually on how it works. Of taking chains all the way back until you find something where it should go. Oh, I should pause.
Yeah, but if there are no questions, we're all free. We're all good now.